All right, let's talk about three algorithms that are the absolute bread and butter of technical interviews: bubble, selection, and insertion sort. You've probably heard of them, but if you've ever wanted a super clear, no-nonsense breakdown of how they really work, and more importantly, how to talk about them in an interview, well, you're in the right place. Let's dive in.
So here's our game plan. We'll kick things off with the basic problem we're trying to solve. Then, we'll introduce our three sorting contenders. After that, we'll put them in the ring for a head-to-head comparison. And we'll finish up with the stuff you really need to know to nail this part of your interview.
Okay, let's get right to the heart of it. Imagine this. You're handed a list of numbers, and it's a total mess. The task seems simple enough, right? Just put them in order. But the real question, the one interviewers care about, is how you do it. Your method says a ton about how you approach and solve problems.
So why is this such a classic interview question? I mean, let's be real. Nobody's using bubble sort to organize a massive real-world database. But that's not the point. The point is to see how you think. Can you break a problem down step by step? Can you turn that logic into code that actually works? And crucially, can you talk about the pros and cons of your approach? That's the real test.
All right, it's time to meet the stars of our show. We have three fundamental sorting algorithms, and it helps to think of them as having their own unique personalities. First, you've got bubble sort, the simple, straightforward one. Then there's selection sort, the slow and methodical searcher. And finally, insertion sort, who's kind of like a strategic card player.
First up is bubble sort. This one is probably the easiest to understand. Its strategy is dead simple. Just look at two elements right next to each other. Are they in the wrong order? Yep. Okay, swap them. It just keeps doing this over and over, and as it does, the biggest values slowly bubble their way up to the end of the list.
Let me break that down. You start at the very beginning of the list. You compare the first and second numbers, swap if you need to. Then you slide over, compare the second and third, swap if you need to. You just inch your way down the entire list like that. After one complete pass, you're guaranteed to have the single largest number sitting in its correct spot at the very end. Then you just do it all over again for the rest of the list.
And here's exactly what that looks like. We're looking at the first pair, 5 and 1. Is 5 greater than 1? Yes, so they're in the wrong order. All we do is swap them. Now it's 1, then 5. Simple as that. Now we move on to compare 5 and 4. Fast forward to the end of that very first pass, and look what happened. The number 8, which was the largest value, has bubbled all the way to the end. It's now in its final resting place. It is sorted, it's locked in, and we can completely ignore it from now on and just focus on the rest of the messy list.
Okay, on to our next contender, selection sort. This one has a completely different philosophy. It doesn't care about little local swaps. Instead, it's on a mission. It wants to scan the whole list, find the absolute smallest element, and drag it all the way to the front.
The process here is super disciplined. First, you scan the entire unsorted list to find the one single minimum value. Got it? Good. Now you swap it with whatever is sitting in the first position. And just like that, the first spot is now sorted. You never have to touch it again. Then, you move to the second position and do the exact same thing. Find the smallest value in the rest of the list and swap it into that second spot. You just keep repeating this until the whole thing's in order.
So let's watch it in action. Selection sort starts its scan. It looks at 64, then 25, 12, 22, and bingo, it finds 11. It now knows that 11 is the smallest number in this entire list, and that's the one it's going to move.
And then it makes one single decisive swap. The 11 it found trades places with the 64 at the beginning. And boom, just like that, the first element of our array is sorted. Our little sorted section on the left has started, and now we can just focus on sorting the rest of the numbers.
And that brings us to our final contender, insertion sort. Honestly, the best way to get this one is to just think about how you sort a hand of playing cards. You kind of hold the sorted cards in your hand, and as you get a new card, you find the right spot for it and just slide it in.
So here's the logic. You basically pretend the very first element is already a sorted list, just with one item. Then you grab the second element, we'll call that our key. You compare that key backwards with your sorted list, shifting any bigger elements one spot to the right to make room, until you find the perfect spot to slide your key in.
Let's look at this. Imagine the left side is your sorted hand of cards. Now, you pick up the next card from the unsorted pile. In this case, our key is the number 11. Our whole goal now is to figure out where this 11 belongs in our sorted hand.
So we take our key 11 and we start comparing it backwards. Is it smaller than 13? Yep. So we shift the 13 over to make space. Is it smaller than 12? Yep. We shift the 12 over too. Is it smaller than 5? Nope. Okay, we found our spot. We just slide the 11 right in between the 5 and the 12. Our sorted hand just grew by 1 card.
Okay, introductions are over. Now it's time for the main event, the face-off. This is where we break down the nitty-gritty details, the kind of stuff that will make you sound like you really know what you're talking about in an interview.
Now, I know this table looks a bit technical, but let's walk through it. Time complexity is just a fancy way of asking how slow the algorithm gets as the list gets bigger. That O of n squared you see for the worst case, that's not great. It means if you double the list size, the sorting time roughly quadruples. Yikes. Space, on the other hand, is great for all three. O of 1 means they sort in place without needing a bunch of extra memory. And finally, stability. A stable sort keeps items with equal values in their original order. Notice selection sort is the odd one out here. It's not stable.
But here, this is probably the most important takeaway of them all. Look at the best case time. Insertion sort can be incredibly fast, O of n, if the list is already almost sorted. Think about it. If you're just picking up a card and it only needs to move 1 or 2 spots, that's super quick. Selection sort, on the other hand, gets no benefit at all. It's so methodical, it has to scan the entire rest of the list every single time, even if it's already perfect.
All right, let's bring it all home. We have all this great knowledge, but how do we turn it into a killer interview performance? Let's talk strategy.
Here's your checklist. These are the points you want to hit. You should be able to talk about time and space complexity. You need to explain what stability is and why you might care about it. Make sure you mention that these are all in-place sorts. And for the real bonus points, you absolutely have to bring up that special case where insertion sort crushes it on nearly sorted data.
And now for what not to do. Under pressure, it is so easy to make an off-by-1 error in your loops, so double, even triple check your code. Always think about edge cases. What happens if the list is empty or has only one number? And please, don't mix up the stability. Remember, selection sort is the unstable one. Getting that wrong is a common slip-up. Want one more pro tip to really stand out? When you're talking about bubble sort, mention that you can optimize it. You can add a simple little flag. During a pass, if you don't make a single swap, what does that mean? It means the list is already sorted, so you can just stop early. Mentioning that little detail shows you're not just reciting facts, you're thinking about efficiency.
So there you have it. You've now got a really solid handle on these 3 foundational sorting algorithms. They are essential building blocks, but they have their limits, which leads us to the final big picture question. What happens when your list doesn't have 10 items, but 10 million? That's when these algorithms just won't cut it, and you have to call in the real champions, like merge sort and quick sort, to handle that kind of scale.